to see the string. That's the way. Yeah.
Hello, everybody. Welcome to this week's Astro Coffee Hangout. My name is Tony Darnell from deepastronomy.space, and today, if you care about the planet Mercury, then this is the hangout for you, because we're going to be talking with astronomers from the Goddard Space Flight Center who look at Mercury, and they tell it, and they've learned some amazingly cool things about it. We're going to learn about some. I didn't even know really that there was a thin, sort of tenuous kind of exosphere around Mercury. And if you don't know what an exosphere is, that's fine, because I don't either. We're going to learn what that is today, and we're going to be talking with our guests about all kinds of stuff related to Mercury. And but before I get to my guests, I want to start by introducing my co-host, Dr. Carol Christian. Hi, Carol.
Hello. How are you?
I'm good, thank you. Why don't you start by giving everybody a quick rundown on introduce our Hangout forum.
Sure. The Hangout forum is very informal. We are discussing with astronomers who are doing some cutting-edge research with a variety of instrumentation, and we learn about what we're thinking about, how they made observations, how they made models, and what they discovered from it. And so we're very fortunate today to have some researchers on Mercury, and the Hangouts are brought to us by the American Astronomical Society and the American Astronautical Society. So astronomers and engineers supporting this lovely informal discussion about the latest science.
That's right, great. And so I want to remind everybody that that we want you guys to interact with us. We want to leave questions and comments. So please do that on whatever platform you're on. You guys know by now where I'm streaming. You guys know all that. I'm looking at the live chat on YouTube and Facebook and Twitch. So just leave your questions and comments there, and I'll be happy to read them off to our guests. And hopefully you guys can interact and get some knowledge that you didn't have before about this planet we really don't talk about all that much. I don't find myself talking about Mercury all that much, so I'm really interested to see what we can learn today. So let me go ahead and get started. So our guests today, let me pull them up. Our guests today are sharing the same camera. On the it's my left. I hope it's not mirrored too much. Raise your hand when I say your name, Dr. Menelaos Sarantos. That's him. Good. Hi, Menelaos. Both of these guys, by the way, are research astrophysicists at Goddard in the heliophysics science division, and they are studying all things within the heliosphere, presumably. And on the right, my right, is Dr. Diego Sanchez. He's also a research astrophysicist. So, hi, guys. Welcome to our Hangout.
Tony, Carol, thanks for having us. What a great forum and great idea.
Yeah, thanks very much for having us.
Yeah, Carol's the one. Carol's the genius behind this one, and I'm very, very grateful that she set that up. So, all right. So, Mercury, why don't you set up today's paper? Now, as Carol said, what we like to do each week is we like to highlight a research paper that's recently come out so that you guys can get access to some of the cutting edge science. So, what paper are we talking about today, guys?
So the paper is entitled Reconciling the Dawn-Dusk Asymmetry in Mercury's Exosphere with the Directionality of Micrometeoroid Impacts.
Oh man, I'm sorry I asked that question.
I call it death by 1,000
reconciling by.
Who's responsible for the reconciling?
For reconciling. Reconciliation is good.
Okay, so maybe in slightly more simple terms, you could tell us a little bit about what your paper's about.
Right. So we had wonderful measurements. We had a very successful mission called Messenger, NASA did, flying around Mercury from 2009 to early 2011. The spacecraft survived scorching temperatures very near the sun, near a very bright planet with temperatures 700 degrees Kelvin, almost 1,000 degrees Celsius. And it survived for 4 years and took wonderful measurements. Among others, we measured the light emission or light scattering, if you wish, from a very thin, collisionless atmosphere around Mercury. So in the absence of any atmosphere, both solar wind particles as well as incoming dust can reach the soil and vaporize it. And that we can measure. We measured metals such as sodium, magnesium, and calcium in the atmosphere of Mercury. These earliest bodies have very much, there's a whole set of atmospheres. Maybe it's the most common type of atmosphere in the solar system, surrounding earliest bodies such as Mercury, the Moon, asteroids, icy moons of Jupiter and Saturn. So when you combine all this, this could be very well be the most common type of atmosphere.
Okay, I want to go back to that. So an exosphere is around an airless body, and it's made up of what again? What's
It is the area of an atmosphere, even the topside atmosphere of a planet like Mars or Earth. It is where the atmosphere starts streaming out, and atmospheric gases are no longer subject to collisions. They're as likely to escape to space as they are to collide with each other. So that's really what the classical definition of an exosphere is.
It's just a bunch of stuff then, right?
But it is gas escaping out to space. Now, when it comes down to this airless bodies, though, this starts all the way down to the surface. At Earth, it starts somewhere like 400 kilometers above the surface of Earth.
Our airless surface starts 400 kilometers above us.
But for Mercury, the Moon, this starts all the way from the surface up. Gases essentially freely escape.
So does that mean that every planet has an exosphere, essentially? Is that what you're saying? Okay.
Yes. It either starts from the surface or somewhere.
Right, if there's no
True.
atmosphere as we think of it.
That's
Okay.
right. That's right.
Hmm.
So in a way, everybody will have a sort of atmosphere. The difference with early like bodies like the Moon or Mercury is that they don't have this bound atmosphere, gravitationally bound atmosphere like we do on Earth.
Right.
So everything that comes out of the surface will escape, will be able to escape.
So these types of atmospheres must be supplied continuously. Every second, new gases must be emitted in order for us to see something.
And this is done because Mercury is so close to the sun? Is that where it's coming from? Or why? How is Mercury doing this?
It is dust and the solar wind that's doing it.
Solar wind, okay.
You do get, simply these temperatures are high enough that probably some material in the mineral phase can easily seep out. But mostly you need something energetic to vaporize the soil. I mean, most of these rocks don't melt until 1,000 degrees or so.
Okay.
But that's yes, Tony.
I just wanted to ask you, I want to go back to Messenger in just a minute, but before I do, give us some basics on Mercury right now. Can you tell us a little bit about what it's like? What's its temperature range? What do we know about Mercury as a planet right now?
It's very hot and very cold at the same time. The night side of the planet, and it stays in the night side for 50, 30, 40 days. I think the period is 88 days. So for about 40 days, when you're on the night side, you're exposed to 100 degrees Kelvin. Absolutely, everything freezes out. On the day side, though, and again, you're exposed to sunlight for about 40 days, it is 725 degrees Kelvin when Mercury is at the closest point to the sun. It's perihelion. And about as hot, maybe 600 degrees Kelvin, when it's further away from the sun. It's very eccentric. It has a very eccentric orbit, and it is this eccentricity, in fact, that creates some of the variation that you see in our dust model, the impact of dust on Mercury. So that's definitely something we know. It has a magnetic field that is strong enough to deflect the solar wind from most of its surface, but it still leaves the polar regions unprotected to this streaming solar wind ionized material. So both the dust then and the solar wind can reach the surface and vaporize material.
How strong is the solar or is the magnetic field compared to, say, Earth's?
I think it's 10,000 times less strong.
Less strong. Okay.
Yeah, it really is able to deflect the solar wind.
And does Mercury have a core like the Earth does, like a dynamo that generates that, or?
That generates the magnetic field, and in fact, Mercury has a huge. The reason this dipole has survived is because it almost makes it all the way. The molten part almost makes it 2/3 of the way to the surface. So the core of the planet, what's full of metals, iron in particular, extends 2/3 of its way to the crust. So it's a very large area inside the planet that remains molten billions of years later and sustains this magnetic field.
And would you say that there are, like, when it comes to things like mineable materials, things like metals and things like that, Mercury's pretty well off? Got a lot of that stuff in it.
One of the findings of MESSENGER was, in fact, that there were more volatile materials than expected, and that ties to formation theories.
What are volatile materials? What do you mean by that?
Things like sodium, for instance. Things that should have escaped. They're easy to lose to space over billions of years. Yet these elements still reside in rock today. The other major finding by MESSENGER was that we found water ice in the permanently shadowed regions of Mercury. So even though it's scorching hot, in the polar regions there are craters that are never exposed to the sun, and we found solid evidence of water ice in these regions.
Really? So there's liquid water?
There's water ice.
Or water ice, which is not liquid, right? So got it. Okay, sorry. You said water ice. I heard liquid, and I was like, I don't know.
Yeah. So in
H2O ice.
Got it. Thank you, Carol.
I'm sure there's other volatile materials. There is carbon dioxide, all kinds. It must be dirty ice. And I want to point out that in addition to the NASA mission that ended in 2015, the European Space Agency is getting ready to send a spacecraft to Mercury, a dual spacecraft. We'll have, in other words, 2 spacecraft mission. It's called Bepi Colombo, after a famous Italian astronomer. And it's going to launch next year, 2018. I believe it will take 7 years, just like MESSENGER, to get to Mercury. So sometime at 2025, we'll be hearing a lot more about Mercury again.
Okay. All right.
But Diego and I and other people, and Peter, whom we missed today, we intend to keep Mercury in the headlines for as long as we can.
Yeah.
So you said something earlier about when you were talking about the temperature ranges of the planet, that you said something about every 40 days when the other parts of the planet becomes exposed to the sun, it gets these temperatures. What's the 40-day thing all about?
So that's a great question, Tony. So basically, if you were on the surface of Mercury, the sun would stand still for about 30 days or so. It wouldn't move. It would be at noon continuously for about a month. So, and then the surface starts rotating quite quickly, and that's what gives you the 40 days. It's called a 3-2 resonance. So it rotates 3 times around its axis for every 2 passes through the sun, or vice versa.
And its year is how long?
In order to go for a whole day, it has to travel around the sun significantly.
Yeah, in order for the same point of the surface to be back at noon, you have the 2 Mercury years have to pass, 2 full revolutions of Mercury around the sun.
Good. All right. Well, that's hard to visualize, isn't it? So so you're sitting there for a month with the sun high in the sky, giving you an intense sunburn.
Yes.
And then, but that makes it seem like it's got variable rotation rates. Suddenly it starts to...
With respect to the sun, yes.
Okay. And that's that resonance thing in operation, right? You don't notice it until you reach a certain point in the resonance of the orbit, and then you start really whipping around.
That's right.
That's weird.
In fact, if you stood at a place on Mercury, you would find out that the sun almost counter-rotated for a few days. It would start moving away from noon and back to the east until it started moving to the west.
Kind of like a retrograde for the sun, right?
Yeah, that's exactly, yes. It's very strange.
It is strange. I never really thought about it that way, but that's really odd. Okay, well, you said, I want to get back to Messenger and then your research. So Messenger was, as I understand it, and correct me if I'm wrong, the impetus besides a lot of the data that you currently have now. Messenger was a NASA satellite, and you said its mission ended in 2015?
Mm-hmm.
Okay, so what were some of the instruments that were on it? Just very briefly, what did it have on it?
There were magnetometers to measure.
Okay, to measure magnetic field.
We found that the dipole is shifted off the equator considerably. A plasma analyzer, so we measured the composition of the ionized atmosphere, as well as the solar wind component. There was an ultraviolet spectrometer, which measured the emission from these atmospheric gases that I study in particular. There were energetic electron measurements. So we wanted to study the effect of the magnetospheric processes and their effect on space weathering, which is the weathering of the surface, and as well as their connection to the atmosphere. There were, of course, cameras producing a laser altimeter producing very high-resolution topographic models of the
I
surface.
remember seeing those actually, yeah.
Right.
When they came out.
There was the same instrument that did the UV spectroscopy also detected the reflectance from the planet, and from that you can make compositional analysis. There was a gamma ray spectrometer and an X-ray spectrometer. Again, this measured the composition of the surface down to 1 centimeter or so. So we have a very good understanding now of the compositional units on Mercury, and we find differences in things like magnesium, for instance. The northern region appears to be more dense in certain elements. So I think that probably covers most of the instrumentation that I remember.
Right. Okay, good.
Could
Thank you.
I ask a question back on the rotation? So is Mercury rotation axis tilted with respect to the orbital? Like Earth is 23 degrees.
So the sun moves less than a degree up and south of its equator. So basically,
it's pretty.
It's in the path of the moon. I mean, on the moon, the sun moves about 1.5 degrees over the year north-south. But Mercury, even less.
Okay.
There's no tilt.
Interesting.
Okay, so I want to get to a couple of questions. Jambo Bug Hunter on Facebook is asking, does Mercury have craters with ice in them? I read something, maybe misunderstood the article, as have a medical background. This person has a medical background. The only bad question is one not asked. That's right, Jambo. So does Mercury have craters with ice in them?
Yeah.
Yes.
He said that.
For reasons we could see this in the northern hemisphere because that's where the periapsis, the closest point in Messenger's trajectory was. There was evidence from ground-based observations, radar scattering indicated that there's something like ice in these permanently shattered regions. And we did confirm it and make the case a lot stronger with Messenger.
Great. And I had to read that out because Jambo's from Zephyr Hills, Florida, my neck of the woods. So, yeah, homeboy here. Okay. Adam Synergy, I'm going to ask your question, but I don't understand it, Adam, so maybe these guys do. What makes Mercury's hollows? Does that make sense to you?
Oh, yes.
Well, first of all, tell me what that means. I don't understand what it means, and then answer.
First, let me preface by my saying I'm not a geologist, but hollows were freshly exposed areas. It looks like they're sublimating. Something is eating them away. So this is material that there are fresh holes, if you wish, in the ground, and we could see these areas they're spotty. They're very small, maybe 1 degree, and they're dispersed throughout the planet, but they appear to be geologically active in the sense that they are losing material today to space. And in fact, part of our search with the atmospheric instruments to see if we could see the vapor present-day vapor above these areas. And the search, as far as I can tell, is not conclusive.
Okay.
Do you know if it's a different composition than the rest of the surface, or it's the same stuff?
I believe there is supposed to be sulfide, so they must have found a lot more sulfur than anticipated on Mercury.
Oh.
And these compounds are volatile: calcium sulfide, magnesium sulfide. So we think, or at least that's my understanding from the messenger team, is that these are the elements that somehow are exposed. The compounds that are exposed and now are getting lost to space. As I said, it's their cause. Expose these volatiles to start vaporizing.
Okay, I'm going to ask a question from Joe Schmo, and then Diego, I want you to go first on this one, okay? You're awful quiet over there. Joe Schmo is asking, heard a couple of theories about why... Huh?
He's the Mercury expert.
Yes, but you're also here part of the paper, so we want to hear what your thoughts are too. And this is a good chance. Heard a couple of theories about why Mercury has larger than expected core and magnetic field, from a big impact vaporizing outer crust to solar wind eroding the crust. Do you guys have a favorite theory about why it has a larger than expected core and magnetic field? First of all, was it larger than expected? You're still going to Menelaus? Okay. All right, Diego. I'm trying to get you in it, Diego.
No, it's interesting because the way this work started was, and I'm sorry I'm digressing from the question here, but the way this collaboration started with Menelaus and I and Peter is that my expertise is on meteors on Earth. So
okay, we're going to get to that soon. Then okay.
We want to hear about that. I want to hear about that.
That's
all
why,
right. We need to get off Mercury, is what you're saying first.
He was if there are meteors on Earth, there should be on Mercury too, and that's where our collaboration started. So I'm just learning the details of Mercury science, but I can't say I'm an expert on the planet geology. So.
All right, fine. Well, we'll get to those meteorites in just a minute, and but let's get to this. Let's get to Joe Schmo's question. So, what about this? What this larger than expected magnetic field and core?
Yeah, as I said, it's very large. I mean, it gets 2/3 or even more. I think maybe 80% to the surface. I mean, it starts just a couple hundred kilometers below this core, this metallic core. Starts a couple hundred kilometers below the surface. I mean, Mercury has its radius is about 2,400 kilometers. So if 80% is the core, that's maybe a few hundred kilometers beneath the surface is when the metallic core starts. I'm not very familiar with the theories. I have to say that I must read myself on what made this core retain the heat for so long. Clearly, the reason we see the magnetic field today is because the core remains hot, and as it rotates, it produces this magnetic field. It must have something to do with the origin of Mercury and how it retained the particular materials that you need. Generally, you need some radioactive materials to keep the core going. But I must say, just like Diego, this isn't my cup of tea, if you wish.
Okay, well, let's get to what is your cup of tea then. Let's talk about the paper that you guys, and I've got these animations. I'm happy to put them up. I'm also happy to put up your slides when you're ready to talk about them. So here we have Mercury. We've learned a little bit about the planet itself, its resonance, and just to read out a comment from Bill Druin, he goes, a lot about rotation, resonance, and daytimes made no sense at all. And then I looked up Mercury's orbital eccentricity. So yeah, that was they also talked about that too, Bill, when they said about how eccentric the orbit was. Okay, so let's leave Mercury now and talk a little bit about what these meteoroids are all about. And Diego, you want to start?
Yeah, sure. What Menelaus was referring as dust before, it actually dust implies a very, very, very small particles. These are more on the category of meteoroids. We're talking about particles that are about a little bit less than a milligram in size, like a grain of sand. And they originate from comets and asteroids, collision and disintegration, and they orbit the solar system. And we know a lot about these particles because when they hit the Earth atmosphere, they produce meteors, and we know all about meteors and meteor showers on Earth. Now, these particles, the ones that we're used to see as shooting stars here on Earth, they are a little bit bigger. The ones we are talking about are small. So if they would come on Earth, they would come on the atmosphere, they wouldn't actually produce light. They're so small that they would just burn without producing any light that can be seen with the naked eye. But it turns out that these are the bulk of material out there. And they come into these planets every day, providing very large amount of fluxes. Like we're talking about 40 tons or so of mass comes into the atmosphere every day due to this very small. That's a great picture to show from these sun grains, and so that was my expertise when I actually got to meet Menelos here at Goddard, and then he said, "Well, what about other planets? I mean, these dust are all over the solar system. How would this affect the moon? How this affect Mercury?" And that's the project we got involved in this paper. Is we have these models of these particles hitting the Earth, and they come from very specific directions. The directions are associated with the type of comet they were produced from, they originated from.
Population.
That's right. These directions. So there are several type of what is called family of comets that produce this dust, and depending where they're coming from, they will have preferred directionality. So we use these models that we had on Earth, and we expand them to see how they would affect other places in the solar systems. In the case of this paper for Mercury, and see how it varies along the orbit of Mercury. And we found that it not only varies a lot, but it actually produces the effects that Messenger was observing that were very puzzling before actually applying these models.
So the only addition I would make for now to what Diego said is that these aren't just models. These are models that have been validated at Earth with this radar measurements. There's also scattering by the zodiacal light, remote sensing. So for decades now, we've been collecting these measurements about the distribution of dust throughout the solar system. And these models of dynamical models of dust. So these are test particles we follow in a computer for millions of years. And locations of planets are updated. And we follow these test particles until they either fall into the sun or escape the solar system.
Or they hit the planet.
Or they hit a planet. And so they've been proving successful in reproducing some of the measurements we get here at Earth. And our objective for this collaboration and for this project in general is, can we combine these radar measurements, the constraints that we have from Earth? We evidently had a giant collector of dust particles in the form of Mercury. These dust particles hit the planet, they vaporize it. We were measuring the vapor around the atmosphere. Well, can we use this as a calibrator, another calibrator? For
use this model as a calibrator, you mean?
Well, right. Use the measurements
to calibrate
them
okay.
to understand
even
that.
Better.
That's right. That's right.
All right, so I just want to, is this, to make sure I'm showing something that makes sense, is this a model?
No, those are observations.
These are the observations from Messenger.
No, those are observations for with two radars. One in southern Argentina that I use, and one in northern Canada.
Okay. Well, maybe I don't want to confuse things while you're talking. I just thought maybe I was.
No, that's fine.
This is Earth. This is Earth. This is what we see from Earth.
Yeah. So if you the way to explain this map is, imagine you are driving you're driving your car, and the direction you are driving is where it says 270 is the center of that map. That's the direction you are going. That's called the apex of the Earth. It's the direction of motion of the Earth.
Right here, yep.
That's right. So the enhancements you see there,
these red areas.
Those red areas in the center are the directions where most of the meteors come from. So you have, for example, just a little bit above this 270 and just a little bit below the 270, they are called the north and south apex sources. So those are meteoroids that hit Earth directly from the front. They ram into the planet as the planet moves along its orbits.
Okay, so we've got these radar. We've got radar that not too unlike what a policeman uses to see how fast you're going.
These are significantly bigger.
But bigger, and we're pointing them up at the sky, and we're measuring these little tiny grain-sized particles that you're calling meteoroids.
Yeah.
And we're seeing based on our direction of travel, which, as you said in that map, was the center, and we're seeing where they all come from in different parts, and you're measuring not only where they are, but what do the colors mean? What this red and green is that a speed by any chance, or
no, that in this case is intensity. So you can see that the two most intense sources there, that is a little bit next to the sun and the other one on the opposite side, those are the most dominant sources. They are called the helium and antihelium sources, and they are composed of meteoroids that come from comets with short periods. They are called Jupiter family comets, and these are the 80% of the meteoroids on the solar system come from these sources. And if you want to see those, it's like these particles are hitting the planet from the side. So if you are going into the direction of the 270 of the center of that map, the meteors from the helium and antihelium hit the Earth on the sides of the planet, and so that what you see in the colors there are actually the intensity. You are more intense, those sources, than the sources on the apex.
So even though you're running into the stuff at 270, it's actually, there's more flux from the sides.
Coming from the sides.
From the sun and from the anti-sun or whatever.
Yeah, that's right.
So
wow, that's interesting.
Yeah, really. So here we are looking at stuff that is coming from the Earth using radar, which I think that just to be able to detect these kinds of particles like this with radar.
That's a lot. So we don't detect the actually little particle. So the little particle is called a meteoroid. What we detect with the radar is the meteor. And the meteor is, as this particle comes into the Earth's atmosphere.
Oh yeah, that's right.
Ionized air.
What something is changes when depending on where we see it. Yeah, I always forget that.
If you remember the shooting star, when you see a shooting star in the sky, you don't see the particle. You just see the train of light that particle produces entering the atmosphere. So with the radar, it's the same thing. When they come in, they will produce a train of ionization. Because they hit the air molecules at a really high speed, so they excite them and they release electrons and they produce a train of ionization. So the radar detects that ionization.
Okay,
So here's the cool thing about Mercury before we show this comparison.
Okay.
So you heard Diego talk about all the limitations of these measurements at Earth. You have to ionize it. You probably don't volatilize the grains. That's why we find micrometeoroids in Antarctica, for instance. They survive entry to the Earth's atmosphere. Now, transfer this dust particle, this dust bullet. It hits Mercury. It hits Mercury with something like 60 to 80 kilometers per second from the apex direction. When it gets to the soil, it kicks up a volume of vapor that's proportional to the second power of its velocity. So that acts as an effective magnifier. It's a big amplifier, rather. And that's why we can measure this the effect of this dust meteor so much more easily on Mercury. And that was the initial impetus of our work. So you vaporize a lot more material than you brought in on Mercury, and so it's easier to see it. And so we thought this would be a great constraint for all these models. And in addition, we have these puzzling measurements from the atmosphere. We were seeing a lot of motion in the atmosphere. And it was unclear why would this be so.
Yeah, so that basically that's the advantage of studying these things on these meteoroids in planets like Mercury or the Moon. By not having an atmosphere, they are not being decelerated, they are not being burned out on the top of the atmosphere. They just hit the body with the impact velocity they have in space, and producing this amplifying effect that Menelos just mentioned. But essentially are the same bodies that produce the same particles that produce different effects in the different bodies depending on if they have or not atmospheres.
Okay. Is now a good time to show this? Because what I like about this slide is that you have your model that we showed earlier over here, which is what you were trying to calibrate versus over here. I always like to see this data on one side, and also like to see that, wow, that looks pretty darn close to what you thought. So this again is Earth, right?
That's the data on Earth, yes.
Right. So your model looks to be like it's pretty spot on, or at least pretty darn close.
Yes.
Okay. What about Mercury then? How can we make the transition from what we see on Mercury versus the observations?
Well, that's the one of the movies that you have. The one.
Which one should I show? The first one or the second?
I don't remember what the first one is.
Well, all right. Let me put
that one. That one.
All right.
So it's the equivalent of what we were seeing from Earth. You know, the direction of arrival. This is the equivalent on Mercury. But now imagine that the middle of your screen is the sun direction. So the sun is coming from 1200 hours. So that's the so-called subsolar point. This is the portion of the planet facing the sun. And 6 a.m. is
the apex.
6 a.m. is the apex. Call it morning. 1800 is evening. And what's left and right of your screen then is the night side.
Yeah. So what you can see in this movie is, the difference of these movies, the coordinates are a little bit rotated from the plots that you show before. But if you remember in the plot before, I say the 270 is the direction of motion of the planet. In this case, it's shifted to what the 6 hours local time. That's the direction the planet is moving. And because the Mercury orbit is so different than Earth, the orbit of Earth is so eccentric and it has some inclination, the way that the sources are going to hit the planet varies much more dramatically than the way that they vary on Earth.
Yeah, that's a lot different. Boy, the pole or the equator is really getting hammered here. It looks like.
Yeah, you can see that the equator sort of moves back and forth. You can see that the helium source is super intense during half of the year, while the anti-helium is not as intense. It's a much more, the variability is much more dramatic than what you can see on the planet. And this is basically a combination between what we know from Earth on where where the meteoroids are distributed and what their orbits are, and the very particular orbit of Mercury.
Right. So what is shown here is a full Mercury year, and it keeps playing. And TAA that the movie shows, it stands for Mercury True Anomaly Angle. When that is 0, that means the planet is at its perihelion. It's closest to the sun. And
True anomaly angle?
Yes. True anomaly angle.
I have one of those. No, I'm sorry.
So this shows a full year there, and the color scheme is the same. And basically what the figure says is when Mercury moves towards the sun, most dust is impacting from the day side almost from 10 a.m. Or so, almost near the subsolar point, and vice versa. For the part of the year that Mercury moves away from the sun and towards its aphelion, the dust now begins to impact primarily on the night side.
Okay, so around 200, 250, we see it from one side, and around 0, we see it from, I see. So it's moving away.
That's right.
And then it sort of calms down, like now. Then
and near, when it's near perihelion, you'll see that, the source is almost balanced out. It's not as clear in this one because this actually, again, shows the different populations, and because the short period comet, the dust from short period comets is the most numerous, you never quite see the apex source show up here. Now, recall though that this is only half of the picture. The other half is the velocities with which these particles arrive. And this is really what we detect in the atmosphere indirectly. It is the product, if you wish, of the number of dust particles arriving at each one of these surface elements of Mercury times a function of their velocity. And the vapor is really something, the velocity to the second power, a little bit more stiff. So another movie, the next movie that we have there.
Before you leave this, when you say vaporization, you're talking about both the incoming particles and the surface, or only one of those?
What he's like, what Menelaus was talking earlier about this amplification effect on the surface. So you have a meteoroid, it hits the surface, and then they produce this vapor coming out from that collision. If the meteor is it's small but really fast, it will produce a lot of vaporization that if it would be very small.
So most of the material is from the surface?
By far, yes.
Yeah. Okay.
The material that messengers observes come from the surface, from the vaporization of the surface, yes. And so what Menelaus is referring now is when we then go and the picture that the movie we were showing is just, we see these the helium and antihelium sources very strong, but those are usually lower velocity meteors. So even though the apex source is weak in the movie we show, those meteors will have much higher velocities because they basically hit the Earth from the front. It's like what as a grad student we used to call the bug in the windshield effect. Your windshield, because you're running into these things.
Yep.
So the effect that the smaller population of particles coming from the apex will have on the surface of the planet will be bigger than the ones coming from the side because their velocity is so much higher. So, and that is what is shown in the next movie.
Okay, here we go.
So what you see there is what you see there is like, if imagine you standing on the surface of the planet and the colors
facing the sun again,
and the colors are the intensity of vapor coming out of the surface when particles hit the Earth. So that red blob that you see moving is basically where the most of the vaporization occurs, and is basically where these very fast meteors is hitting the Earth. And you can see that throughout the Mercurian year, it moves. Sometimes it's centered at 6 a.m, sometimes it's centered closer to noon. It varies quite a bit, and this is
predictable. Various predictably is the important word here.
Yeah, and these were the variability that messenger observed, and before we applied these models, were unexplained.
I don't know about you guys, but I feel like I need to have Jefferson Airplane playing while I watch this.
Yeah, I know. It's pretty good.
I'm
going to apologize to everyone. I have to go see what my students are doing.
Oh, okay. Thanks, Carol. Appreciate it. Thanks for joining us.
All right, good seeing you.
Thank you.
Thanks a lot.
Bye-bye.
Yeah, so this is really hypnotic. Okay, well, all right. So I want to I want to get to a couple of. Let me get this going. There we go. There. Okay. So, I want to get to a couple of questions before we run out of time. Denny T is asking: is the core mainly composed of iron? This is Mercury's core. Do you guys know?
Yes, it's even though the surface apparently is devoid of iron, it has to be iron. Nickel are the ones that produce magnetic fields that are motion of.
Okay, and Cosmic Stardust, this was back when we were talking about Mercury, was asking, how exactly do you figure out if it even has a core? How do you find that out? If it has a molten core or any kind of core?
I mean, the magnetic field, the presence of the magnetic field, which is measurable, of course implies a core.
Mm-hmm.
That's how large-scale magnetic fields are produced, by the rotation of a molten core inside the planet produces current and therefore a magnetic field.
Right, and by comparison, Mars doesn't have much of one, and implies that it's probably got a
localized.
It used to, and that's why it could sustain an atmosphere. But for some reason, it turned off as planets cool off, their interiors cool off as well, and that stops this rotation of molten material, and that's how a magnetic field dies down.
That's right. Thank goodness for magnetic fields is all I got to say. Adam Synergy is commenting, Mercury, the inner solar system's duster. Yes.
This is really where our program is going. We intend to use these measurements of the atmosphere of Mercury as the big amplifier in the inner solar system. At the same time, something we didn't discuss is how a very recent lunar mission, it was called LADI, Lunar Atmosphere and Dust Environment.
I remember that, yeah.
Yes, you may remember that it launched from the East Coast, and it was a big spectacle. It was a night out here from Cinco Tig. It was a midnight launch, and it could be seen from anywhere, on the East Coast all the way to New York and further out. This mission measured dust around the moon as well as the atmosphere for about 5 months between late 2013 and 2014. And again, the idea is we actually had a dust counter on this mission. And for 5 months, it measured hundreds of thousands of this particulate matter now. So not only vapor, but also particles are ejected from the surface of Mercury and the moon every time these bullets hit that ground. So with Messenger, we do not have a dust counter. The Bepi Colombo mission, the ESA mission, will. But with LADI, we both had a dust counter as well as an ultraviolet spectrometer. So we measured both the atmosphere resulting from this incident dust as well as the solar wind, but also we measured the dust ejecta directly. And again, recall, we have a 10,000 times amplification in the signal. Every time one of these dust bullets hits the moon, it produces 10,000 times more mass that flies, and we were measuring that mass.
That's the amplifying effect you're talking about.
Right.
Yeah.
Yeah. And then, the other interesting part that we are extending all this knowledge to other planets is, for example, in planets with atmospheres like Earth or Mars, this dust is going to evaporate and form metal layers. These metal layers have been studied for a long time here on Earth through various techniques, but some of these metals are being observed now at Mars with MAVEN, with also a NASA mission. So we are actually hopefully getting some data that will help us extend this, understand what is the distribution of all these meteoroids from Mercury using Messenger all the way to even the outer solar system, the outer planets in the solar system with all these different phenomena that these meteors produce in these planets.
Now, with MAVEN, though, is it doing it at the altitude of Mars where it's gas free?
So with MAVEN, it's doing it more or less at the same altitude that happened on Earth. Is where the
but well above Mars' atmosphere.
No, not really. It's about 100 kilometers of altitude. I mean, you need a good amount, dense enough atmosphere so the meteoroids. And remember, these are very small meteors. So they have to encounter enough atmosphere so they can burn out and release atoms into the atmosphere. So in order for you to see the metal layers that are produced from the ablation of these meteoroids, they need to encounter enough atmosphere. So they have to penetrate the Martian atmosphere significantly. It's not at the top of the atmosphere. It's well into the atmosphere. It's down to 100 kilometers, 120 kilometers. I don't remember exactly the altitude now.
So I have a couple questions as well, but you go ahead.
I was going to say, Tony, you either need no atmosphere so they hit the ground, or a lot of atmosphere so they burn up. You can't have something lukewarm, because it will just deposit it to the surface without any effect.
That'll mess you up. Yeah. Okay.
The porridge needs to be really hot, is what you're saying. Right. So the question we have here, we were kind of talking a little bit about stuff that was happening in the outer solar system. So Philip W. asks, would this field of meteoroids be measurable further out in the solar system? For example, would we find a field like this one in the asteroid belt?
Well, yes, actually. What we mentioned before is that we are seeing these different directionalities of meteoroids, and the directionality comes from different families of comets. So as you go out of the solar system, the picture will change a little bit, because some of these comets won't be as effective as producing dust that far out. So, for example, these helium anti-helium sources are formed by comets that they're called Jupiter family comets. They have periods about 20 years long, and their orbit gets all the way up to Jupiter, and they come back to the inner solar system. So if you go beyond Jupiter, these meteoroids are not going to be present, or they're not going to be so significant, and other type of comets or other type of bodies are going to be the more important contributors to meteors, like, for example, Halley-type comets or cloud comets, which are much more longer period comets. So the picture will change depending where you are in the solar system. But in the asteroid belt, that's significantly closer to Earth and Mars and Mercury. That's what we call the inner solar system. That the picture, the models that we have right now can be applicable. That they're probably going to be similar contributions from this.
And kind of along those same veins of the families of comets and dust and things like that in the different regions they come from, Galaxa asks, can we tell,
Galaxia.
if some of this is Galaxia? Sorry. I'm also bad with names.
Yeah.
Is there other sources from interstellar dust? Can we distinguish between comet particles on one side and interstellar and intergalactic dust / radiation on the other? Can we tell where it comes from if it's outside of our solar system? Well,
so in principle, that's a very interesting question, because the search of interstellar meteoroids have been a hotly debated topic in the meteoroid community. In principle, one could say yes if you have if a meteor, in theory, a meteoroid hitting the Earth will have that is in a bound orbit, that is in an orbit, in elliptical orbit in the solar system, will have a velocity, will come into the Earth's atmosphere with a velocity between 11 and 72 kilometers per second. So the question is, if you measure a meteoroid with a velocity much higher than that, in theory, it could be interstellar, because it will be in an elliptical orbit, and it would be coming from a hyperbolic orbit, and would be coming from potentially outside the solar system. The problem is proving that is not an easy task. There are many reasons why a meteor can be accelerated inside of the solar system. Like, for example, getting too close to Jupiter will accelerate it. So one has to trace back the orbit. First of all, it has to measure the velocity with very high precision. That is not very easy to do with the current techniques. Second, one will have to trace the orbit all the way for many, many, many years and ensure that it never encountered any planet or anything that accelerated. So it's a tough problem. But there have been missions with dust detectors that have measured very small, much smaller than the meteors we are talking about, dust that come from the interstellar medium. But that is just, we're talking about nanometer-sized particles. But yeah, that's a very, it's a very hotly debated topic.
I can't imagine tracing back a nanoparticle or meteoroid back through all of these orbits. I mean, that just blows me away. I can see what you mean about it being a hard problem. Any more questions, Carl?
Yes. Going back to Mercury now, cosmic Stardust.
Yes.
Stardust. Oh.
You'll learn these, Carl. You'll learn.
No, the A got turned into a V.
I know, but you can use your imagination.
I thought that okay, never mind.
Cosmic Stardust. That's right, isn't it? Cosmic. That's what you just call her. Cosmic.
Cosmic.
Yeah.
She was asking about how we're able to, how does water form in the craters that don't see sunlight, and wouldn't the ambient heat from the rest of the regolith around it melt the water, or is that ambient regolith also very cold?
That's a very good question. The regolith is really cold. There's a couple of ways you can deposit ice. One would be a big cometary impact, for example, billions of years ago. And one large enough comet meets Mercury, vaporizes, it forms essentially a collisional atmosphere, a real atmosphere, maybe for a few hundred years. And as the water migrates, it eventually, some of it finds its way into these permanently shadowed regions and doesn't evaporate, so it sticks there. And long after the rest of the water atmosphere is gone, now you have all this ice. That's a single catastrophic event. The other way is, what if, for instance, these dust particles that we're measuring, that we're talking about, the small ones, the meteoroids, well, some of them have water, 1 to 10%, as we measure from Antarctica, for instance. If they're not completely dry by the time they get to Mercury, they produce a water vapor, small amounts of it, but over billions of years, they migrate. A fraction of them, again, migrates, finds the poles, and is protected there. And so these are a couple of ways. Also, anytime an oxygen and a hydrogen will be deposited on a grain inside one of these permanently shadowed regions, it's cold enough, but not cold enough to have reaction. So they'll hop around on the surface of a grain, and they'll meet each other and make water. That's how water is made on astrophysical dust.
Amazing. That good question. Good question, Cosmic. Okay, so David Sims, and then we're going to have to cut this off because we're almost out of time. I just want to get his question in because I like it. It's a really good one. Is the dust that falls on Mercury also the dust that makes the zodiacal light? Exactly
that. I mean,
tell us what the zodiacal light is, real fast, if you could.
So the zodiacal light is basically you have meteoroids distributed over the ecliptic plane, the same plane where the planets orbit around the sun, and the sun hits that dust, and it scatters light. So back when you could find a dark night without city lights or anything like that, you could at the right time in early morning you could see this light scattering away in the sky. Sort of you see like a diffuse cloud, and that's basically what is called the zodiacal light. Is light scattered away from the cloud of meteoroids orbiting the sun. So these meteoroids that we're studying is basically the building blocks of the zodiacal cloud, producing the zodiacal light.
Awesome. Okay, we're going to leave it there, except I'm going to just follow up with Peter Quinn's question. Hey, Tony, who's going to be the first to wear a Newcastle United shirt on another planet? How did you know I even had a Newcastle United shirt on? It's like it's blocked by the microphone, but it'll be me. Go Magpies. The first.
I'm a Liverpool fan myself.
Liverpool. Oh yeah. Well, you guys are.
We don't wear the Argentine jersey first.
Yeah, Liverpool, and I don't think Newcastle would probably struggle quite a bit against Liverpool. But that's another hangout, folks. Yes, all right. But I suspect it'll be a Magpie first on Mars. That's just my prediction. Okay, everybody. Well, that is it for this hangout. I want to thank our guests for showing up and telling us about the zodiacal lights and the as well as the meteoroids around the planet Mercury. A lot of great work and a lot of great research is being done. My guests were Dr. Menelaus Sarantos and Dr. Diego Hanches. Both of them were research astrophysicists at Goddard Space Flight Center in the heliophysics division. Why do I want to say heliosphere all the time? And these guys have been looking at Mercury for a while, and they're going to go. What's next for you guys, by the way?
The moon. We are actually focusing.
That's right, with Laddie and that.
Yes.
Okay, great. Well, we hope you'll come back when you write another paper and let us know what's going on with the latest in the research. Okay.
Thanks for having us, Tony. Thank you, folks. Thank you for watching.
Thanks for having us.
Yeah,
it was great meeting y'all.
Yeah, I want to thank all of you guys for participating. I want to thank you guys for asking some really great questions. That is it for this hangout. Ordinarily, I would go over to Twitch, but I'm out of time. I don't have time, but I do want to ask you to call into my station on Anchor on Deep Astronomy and ask your questions. If you download the app and call into my station, I will answer your questions from there. And we will be back next week with our Footsteps to Mars hangout, where we will be talking more about the health effects and the human and physiological challenges of getting our little human tushies to Mars. And so that's where we're going to be picking up next week, so we hope you'll make it. There's also ExoLife Hangout next week as well on Wednesdays. So thank you all so much for watching, and as always, keep looking up.